Okay. Are we started again?
Yeah, it's already started.
Okay. Yeah, so and we have this review of Liouville sectors and fluid, definition of Liouville sector. So the manifold boundary, exact symplectic, the Liouville vector field. It's again kind of going out and in particular parallel to the boundary eventually. And there's some condition which is there is a function on the boundary which is linear in the sense that this Liouville vector field preserves it eventually. And the kind of important condition is that if I take di, this is positive on the characteristic foliage. Okay, if you want to know
the
di, yeah, it's a one form. I guess if I went positive, you complain that I should orient it somehow. But orient it however you want. If you get the wrong answer, you can negate I. Okay, so and let me give you the standard examples. So example. Let's look inside. So we're going to take T star R. And inside here, I'm going to look at the cotangent bundle of the interval 0, 1, let's say. And I'm going to take lambda, so this is going to be this W. And I'm going to take lambda as usual one form, y dx. And if you do that, then z is y dy. Okay, so then this vector field looks like this. And this W looks like this. And this kind of region in W. And okay, let's check these things. Well, indeed, Z is travels along the boundary, in fact everywhere, but in particular outside a compact set. And I just need to produce for you some function, this I. And the function is y. Function y. And let's check. Well, y dy of y is y. Very good. And the characteristic foliation here, the symplectic form vanishes identically. So the characteristic foliation just travels along this thing, and of course y is positive. I mean dy is positive on this direction. So this is a vector. And more generally, there's kind of two classes of examples. So the cotangent bundle of any compact manifolded boundary. And the proof is basically the same as this, because it's this picture times trivial factor. And also more generally, kind of, you could take the products of course, a Liouville manifold is a Liouville sector in a trivial way, it has no boundary. And you can take products of Liouville sectors and round corners. appropriate sense. And straighten. The way you actually think about these things is that any, so the following elementary fact, which is that any Liouville sector near its boundary looks like some lower dimensional Weinstein manifold times, like the kind of half plane. Okay. And this is a half plane. And this last description tells you why this Liouville sector is good for Floer theory, because it means that any disk which begins life inside the Liouville sector, well, it can't get to the boundary because it has to project to this, you can choose a complex structure, which is the standard complex structure on this half plane. And so if the holomorphic disk begins life away from the boundary, it must remain away from the boundary. Usually. Fine, so that's Liouville sectors. What they are for, maybe I should give a couple more examples. So the most relevant kind of examples for us are just surfaces. So I just gave one example, which is this cotangent bundle of this disk, and maybe I'll adopt the convention. So it's kind of, here's some more examples. I could have maybe like a disk with many boundaries. And I'll put these kind of yellow lines for this actual boundary, and these white lines for kind of the places where it goes off to infinity. Okay? So this is an example of a Liouville sector, or maybe I could have some topology in there, like this. But let's keep it like this for a moment, because maybe I want to tell you what the Fukaya category of such things are. So maybe let's begin with this one. Let's begin with this one. Okay, so this one, the Fukaya category is 0. Why is it 0? It's 0 because if I take any Lagrangian whatsoever, I can push it off very far away. And so in particular, if I take two Lagrangians, I can push them far apart from each other, so they have no Homs. And the same argument tells you that the Fukaya category of this kind of half disk is 0. And so the first interesting example is this one. The Fukaya category of this thing is the category of, I don't know, again, it depends what you mean by this, but that's just it's K1 over Z, it's Z modules. And it's a generator, this Lagrangian goes to Z.
So that Barnard did not keep that boundary.
Yeah, when I say Fukaya category of Liouville sector, I guess I should have said, what is the Fukaya category of Liouville sector? Lagrangians, they don't touch the boundary. They should be eventually parallel. They should be eventually parallel to Z, so eventually conical, and we wrap them among Lagrangians of that kind. Okay, so you do wrapping, but you don't get into the boundary. So maybe, let's explain why Hom from this to itself is one-dimensional. the point is that when I wrap this guy, I have to stop at the boundary. Okay, so it has one off of itself. And let's continue a bit. So the next one, this. And this is kind of modules with A2 quiver. This is. Okay, and the reason for that is that, let me exhibit this A2. Here's what Lagrangian. Here's another Lagrangian. And when I compute on between them, so for the same calculation here, each one's endomorphisms is one-dimensional, and maps from this one to this one means I wrap this one, it gets stuck there, but in any case it doesn't talk to that guy. And maps in the other direction, from the orange to the red, then I wrap the orange one, and so it's also one-dimensional. Okay, so then you see that at least I get a functor. I get a functor this way by taking it to modules over the subcategory generated by these two objects, which we just saw was the A2 quiver. Okay. So and now, why is it an isomorphism? I'll tell you the whole story in a second, but what, maybe short of that, you could ask, well, what about this other object over here? Can I at least see how to get that one? And by this kind of discussion we were having yesterday about cones and surgery and so on, well, this one is the cone on the morphism between these two that you see. Because as we were discussing last time, cone is the same as this surgery, and this object is 0, so they're the same. Okay, so that should make it at least plausible that that map is an isomorphism. And maybe in a couple minutes I'll remind you how we know that such maps are isomorphism. And I guess we could just continue with this business if I took this one. Well, there are some Lagrangians in there, and the same kind of considerations as before tell you that category is the A3.
So here's how you make a choice, is you have to favor a few of them.
To choose a particular isomorphism with the A3 quiver.
So does the vector somehow have the cyclic symmetry, is it plain well?
I mean, it is a well-known fact about the A3 quiver that when you take its derived category, it acquires a cyclic symmetry. And this is a geometric instantiation of that fact. Okay. Of course, this is like classical ancient stuff. The way people used to talk about this before, the way people used to talk about this stuff before there was this business of sectors is that they would put a superpotential on this thing, and these various sectors correspond with superpotentials Z, and maybe it's worth saying. So, maybe it's worth saying. I'll just say it first and then discuss. So these correspond to potential Z squared, Z cubed, Z to the fourth, and so on. Okay, so that's how people, that's how you would have meant this. Maybe let me say briefly about the relationship say how the main way that people make this kind of sectors. So, and this kind of a related notion of Liouville pair. And what this is so you have W, Liouville manifold, and the Liouville manifold has what's called its ideal contact boundary. So I said kind of this vector field eventually sweeps out the thing in the cylinder. Ideal contact boundary. And so if you have something in here which is called a Liouville hypersurface, then so the kind of cartoon picture of this is W, this is this kind of boundary, and this is V. Then you get
the boundary was a bottom line before.
yes, that's perfect line. Okay, and then there's V. Then you basically, so what does it mean to be a Liouville hypersurface? It means that for some or equivalently any choice of contact form, the rate flow is transverse to you, and in that case, you can just push yourself a little bit by the Liouville flow and make a sector. Okay, so this. Sweep a bit and V by Liouville flow to make a sector. Not the roll by right.
So it's the same as you take away the legal, this.
Yeah, I delete a little bit neighborhood. Maybe, yeah, you could also, strictly speaking, what I said is a little bit confusing because it's an ideal contact boundary, an honest contact boundary, so maybe a more honest picture is like this. But anyway, you can do some standard thing. In particular, when you have a Lefschetz vibration, when you have a map, from W to C, then you can literally draw this picture and make a Liouville sector. Okay. So it gives. And so what I meant when I was saying that these various pictures correspond to those superpotentials is if you take that map
Which
from
one is V? Given F.
what?
Given F, which was a V?
V is like F inverse. So these pictures you get them by taking this Z to the N and doing this construction. Okay. So the basic facts about Liouville sectors are where am I? The basic facts about the Liouville sector. If we have an inclusion, W prime inclusion of Liouville sectors. And this just means that W is a subset of W prime with the property that the restriction of the one form from W prime onto this guy, it gives it the structure of a Liouville sector. Being a Liouville sector is a property, not a structure. And given such an inclusion, I guess, strictly speaking, it's good to impose the condition that the preimage of the boundary of W prime is a union of boundary components of W. It's allowed also to be empty. But, to the extent that the boundary W meets W, it's a union of boundary components. So under this condition, you get a map from the Fukaya category of W with the Fukaya category of W prime.
So
And
can you
this
draw an
is-
example, which one is not inclusion?
What?
Can you draw an example of inclusion and not inclusion?
So let's go back to this kind of pictures. Let's see. So let's begin with something. Okay. And for instance, this would be an inclusion of the vehicle sector, including the red thing into the yellow thing. So this is an inclusion of sectors. What I was saying about the boundary is just that I don't. It's kind of annoying to think about the following thing. Like, you don't want to do this. Okay, just don't do this. It's really it's still fine, but it's just annoying to think about. Something which is not a subsector. So let's again have this. Again, we made something. Yes. This kind of thing is forbidden. Okay. Because this kind of thing bounded by the pink and the yellow is just not a Liouville sector. In particular, yeah. So okay, so fine. Yes. The key theorem. I was going to explain why you have this map. You have this map basically for obvious reasons. The point is that first of all, if I have Lagrangians inside this kind of pink region, maybe kind of run out of colors here. Some Lagrange inside this pink region. What I was saying before about the behavior of these boundaries tells you that whatever holomorphic disks are involved in computing the A infinity somehow relations, the A infinity structure, in this pink region, they don't leave the pink region. Okay, so if I were to compute this kind of discount in the yellow, it's the same as computing it in the pink. That's the basic fact about Liouville sectors. And then I haven't yet. If that's all they were to say, this map would be an embedding. But it's not an embedding, and the reason is that I haven't yet discussed about wrapping. Okay, so and then the wrapping in the bigger sector could be you wrap more than in the smaller sector. So if you think of what that means, it means there's a map. So, fine. And the main theorem about this stuff, so theorem, so if X is the union of X alpha is a sectorial cover so I haven't told you what this means. What it basically means, so this approximately means that the I mean, first of all, it means all the pieces are sectors. X alpha are sectors, and the kind of corners of intersections, like X alpha intersect X beta and so on, look like products of sectors. Okay, so it's some kind of condition like this. And so the basic theorem, and this is this kind of GPS theorem. It tells you that in this case, the Foucault category of X.
So do you assume that the intersection low dimension or not necessarily?
Same dimension.
Same, the intersection same dimension.
Yeah, same
Okay.
dimension. Is this kind of co-limit of the kind of obvious diagram of this thing. Category X alpha. Right. These are all intersections. X alpha, and the maps come from the inclusions of sectors. Okay, so this is the basic fact of this subject. And let me explain to you why is this fact true. So I said that, kind of by some elementary geometry and some elementary kind of algebra, you reduce to the case of a single overlap. And so we have some picture, and as I said, when you have a single overlap, near the boundaries, the thing has some standard form. So the case of a single overlap means that your picture is like this. So you have some kind of X alpha, X beta, X alpha beta, and this has the property that X alpha beta is like the cotangent bundle of an interval and times some higher dimensions, some lines to know. Okay, this is somehow a feature of what how sectors behave.
This is a global statement.
Okay, let me try something else. Rather than say reduce to the case of let's just reduce to this case. And okay, just as an aside, suppose I had reduced to the case of somehow some single overlap with some mystery region. And the point is that what really does have a standard form is this.
Yeah.
And so then I reduce to kind of this overlap, where the overlap is now standard. So really you can reduce to this kind of. So let's reduce to this case. And now what you do is the following. So the basic move in this game is that you make your life easier by adding stops. So I want to prove, so I want to know that the Fukaya category of this whole thing with alpha x is the colimit of this diagram of Fukaya category x alpha beta maps to Fukaya category x alpha, Fukaya category x beta. Okay, that's what I want. But what I will prove first is a lax version of this statement, where I put stops. How to put it? Maybe here. Yeah. Here. Okay. And the point of doing this is that now the kind of objects in x alpha beta, well, they look like this. And so when I wrap them in this big, so let's call this, when I put these stops, I'll call it x alpha beta tilde. And similarly, x beta tilde and x alpha tilde. And the point is that this x alpha beta, this object now, when I wrap it, it doesn't go anywhere. Okay, so that means, in particular, wrapping it in x alpha beta is the same as wrapping it in x alpha. So, and moreover, it's possible to identify kind of a complement, which is objects that look like this, and those objects, how to say it? They behave. They behave exactly the same.
Yeah.
And on the other hand, I can make the same kind of argument with a whole x. So the Fukaya category of x tilde, and this one has kind of Fukaya category again of x alpha beta. And now you have these two pieces which don't talk to each other because they're these stops that get in the way of the wrapping. Fukaya category of x alpha plus category of x beta. Okay? And so, and now examining these semi-orthogonal decompositions, it is obvious that the Fukaya category of x tilde is the colimit of the corresponding diagram. Because, if I take the map from Fukaya x alpha beta to here and to here, and I take the colimit, you can just compute what it is, and it's this. It has nothing to do with any geometry. Just the geometry enters into convincing yourself that you have these semi-orthogonal decompositions.
So what if you look at those Lagrange which cross?
Which cross like this.
Yeah.
That we discuss later. I mean, that's why I had everyone is a inclusion. Okay, and so then the last thing to say is that I should now remove these stops. And removing these stops, I can do it by taking a quotient by certain objects, as we discussed last time. If I take the quotient by, what does it mean to remove this stop? It means to set this object isomorphic to this object. That means set the cone to 0, and what is the cone? It's this guy. Okay, so I take some certain quotient, and taking this quotient removes all the tildes. But colimits commute with quotients. So that's how you prove it. You put the stops, you make it obvious, and then you remove the stops, and then you say colimits commute with quotients. Okay, and now let me answer. Do you have some question?
No, that was a question.
Okay. Let me answer now this question about these Lagranges that go through. So this this some kind of this explains why, what was this saying? This explains so far why there's a fully faithful embedding like this. And actually, strictly speaking, to get an equivalence, I need another hypothesis. This is by Weinstein sectors. And Weinstein means that there is an exhausting Morris function for which this Liouville vector field is gradient-like. And the consequence of being Weinstein is basically that you have these objects called cocores, which go up, the upwards flow from the critical Morse point. Okay? And so the way that we prove the surjectivity is we just analyze who does it take to generate the Fukaya category of a Weinstein manifold. So a theorem, also by these people, is that cocores generate the Fukaya category of a Weinstein manifold. Okay, and then let me explain the proof. So once you know this fact, then well, these kind of people I was drawing generate anyway, because and how to say it, like if you think what the cocores are, they either live on this side, or they live on this side, or they're kind of single or some vertical thing.
So the condition for Weinstein sector is you don't, everything is like finite or boundary. What is the condition for Weinstein sector? So Weinstein manifold, you have this exhausting function, right? But what do you do with the, what's the condition of the boundary?
Maybe it's best to say that Weinstein sector means the kind of thing I get if I take a Weinstein manifold and I take a Weinstein manifold in its boundary.
You have,
like in this Liouville pair formulation,
yeah.
I take a Weinstein pair. The Weinstein, or in other words, if you want description in terms of the boundary, this boundary, it's R times some symplectic manifold. That symplectic manifold has to also be Weinstein. Just everything has to be Weinstein. So, and the proof of this is the following. I look at the Fukaya category of X, for X of Weinstein manifold. This embeds fully faithfully in the Fukaya category of X times T star R, let's say 0, 1. And the way it embeds is, here's a picture. I have this kind of T star 0, 1 is this thing, right? And I take any Lagrangian in here, and I take it to that Lagrangian times this red line. And it's easy to see that this is an embedding, because how do you compute on in here? Well, you wrap in X and you wrap in here, you get one intersection point downstairs, whatever you do before upstairs. So that's why that's fully faithful. And now this thing is the same by some kind of deformation as X times kind of C with kind of stopped at plus minus infinity. So in other words, since I only care about how am I wrapping, I may as well have drawn instead this picture. And just like kind of contracted these down to points. Okay, that kind of doesn't matter. And so a similar argument, this is the same as the Fukaya category of X times C stopped at what's called the core of X times plus minus infinity. Core of X is everything, so I said there's this Liouville flow kind of goes out. Core of X is everything which doesn't escape under the Liouville flow. Stuff, okay. Or in other words, in this Weinstein setting, it's the kind of all the downward Morse cells. Okay, so like for example, if X is a cotangent bundle, it's the zero section. Okay, and so now we ask, we study this thing, and I ask about what is wrapping like here. Okay, and wrapping here, well, eventually you get stuck at this guy. But what is the price of wrapping past this guy? Well, if I start wrapping past this guy, this guy now is a Legendrian. Because it's this kind of core of a Weinstein manifold with the boundary. And it's a Legendrian whose kind of smooth top dimensional pieces are the downward flows of this Morse function for x. Okay, and so if you think about what happens here, this so it goes and it kind of can't go any further because it's hit this top cell. And so then you can ask, okay, I hit one of the top cells, and then I look at well, what would be the difference between him and him wrapped past that top? I mean, if I just move a little bit more, what would it cost me? And the answer is it's the cone. I mean, to get past this guy, I should take the cone of the copor times this. If I take the cone with the copor times this orange thing, that's the same as taking the red one and wrapping it past that place where it had gotten stuck. By the same kind of argument we kept discussing down. Okay, so that says that at the cost of taking some amount of cones with these copors, I can make this pink one into this pink one. And that pink one is 0. So I proved that this original pink one is isomorphic to some finite complex of these orange guys. But this orange guy is no different than this orange guy. And that was in the image of this map. It was the image of the copor. So I proved that any arbitrary Lagrangian is expressed as a iterated cone on copors. So once you know that, then you can prove whatever you want, basically, about this surjectivity, because you know who generates every one. Okay. So I guess that's. I'll stop there for this review, and then in the next talk we discuss the application problems.
Very good. Very good.
Okay. Welcome to that. Thanks for everyone who's stuck around all this time. I'll talk with this series. I'm going to arrive at. So let me begin with before I state this theorem. So last talk I talked about this kind of sectors and sectorial covers and so on, and then I stated some theorem about if you have a sectorial cover, then you can compute things, but some kind of his, in this business, after we proved this theorem, then for a long time no one made any interesting sectorial covers. So it was kind of a not so useful theorem for some time. The reason that no one made any kind of sectorial covers was that for the most part, whenever you could construct a sectorial cover, you could also just compute the skeleton and then compute microshapes on the skeleton, which was another kind of approach to this local to global business, which was easier. But recently, some people have been making sectorial covers. There was one, someone made one for this like hyperplane complements or something. Were you involved in this?
No. It's tribute
map.
map and
Smith.
and some other makers.
Yeah.
It's tribute map.
Yeah, so the people have started constructing them. And now here's another one. So the theorem, and it'll probably appear in a paper with more people, but it's really a theorem of Peng Shou. So I'm going to just put his name. Probably when it appears in the paper, there'll be other people's names. And the theorem is that there exists a sectorial cover of sim and 0, 1, indexed by expressions and L, C1, CK, and R, where CI and C are the CI are strictly positive integers, and the ends are not strictly positive integers. And so it's indexed by these things, and so now let's call it some U and L and R is inside U. So when I say cover, I'm indexing not only the big pieces, but also the intermediates. Okay, the biggest strata have no C's. It's inside U and prime L and prime R if M, L, and R can be turned into M prime L and prime R by merging adjacent numbers. So for example, like if this is 0, 1, 1, 0, this I could merge, for example, these three and make it 0, 2. Okay, so it exists a sectorial cover like this property, and there's U and L and R is isomorphic. It's not, I say, it's a deformation equivalent, would be better to say, to sim and L T star 0, 1 times sim C1 T star 0, 1 times. Okay? That's the theorem.
What does N has to do with N, L, and N out?
Oh, yeah, sorry. With this, N L plus C1 plus CK plus NR, the sum of all these things is N. This exists such a thing. And let me
So when n is equal to 1, you get 2 comfort?
Now let me just draw you an example. So I'm going to draw the examples. I'll draw n equals 1. This is supposed to be T star 0, 1. And here are these. There's this kind of boundary, and this is this kind of boundary. And this, some region like this will be U 1, 0. Some region will be this, will be U 0, 1, and the region between will be U 0, 1. And then equals 2. So let me, to avoid thinking too carefully about let's call this T star R. I don't want to think about the boundaries. So sim 2, I'm going to consider the map as sim 2R, project out of the 0 section. And sim 2R looks like this. This is sim 2R. I take R times R and I fold it over. And what the cover looks like is there's kind of a piece like this. There is a I'm sorry. There's kind of a piece like this.
Which piece? The upper one?
This one. There's kind of a similar piece going the other way. This piece. And then there's another piece like this. Okay, and these big pieces, the blue piece, okay, maybe I forget which is which, but the blue piece is 0, 2. The red piece is 2, 0. And the yellow piece is 1, 1. And the various intersections of them are 0, 1, 1, 0, 1, 1, 0. There's a 0, 2, 0. And there's a 0, 1, 1, 0. And where are those? This innermost region is 0, 1, 1, 0. Where the yellow meets the blue, well, it has to be something which I can recover to here and here by combining two people, so it must be this one. And so this thing goes everywhere, and this one goes here, here, and this one goes here, and here. That's the indexing of the strata. And the claim is that, so the claim is that first of all, the preimage of this locus in sim2 t star r is in fact a sectorial cover. That's the first statement. And the second statement is that the fiber over a given point has this kind of factorization property, which I said.
The fiber over what?
So if I take a preimage, the claim is its deformation equivalent to this kind of product. Okay. So
when you talk about sectorial, there's always Weinstein's factorial. So
yeah, always one sense. So why is it true? Well, the point is that, so if I wasn't discussing sim2, if I was just taking t star r squared r squared, then we're back in the situation I told you was the one time we knew how to make sectors. Namely, I take any kind of, I didn't say what sectorial cover, but what's true about sectorial cover is if I take any cover of R2 where the boundaries are transverse, then the preimage will be a sectorial cover. Okay, and so that, if we had been discussing kind of just this map, there would be nothing to say. And so the only thing one has to say is near the diagonal. In this space, this map behaves exactly like this map, except along the diagonal. So the only thing to say is what happens near the diagonal. And the point is that near the diagonal, everything comes in transversely to the diagonal. And if you think about what is the local model of the diagonal in a symmetric power, somehow since everything is coming in transversely, it's whatever is happening here is something that's happening one dimension less, where it again looks like a sectorial decomposition times a trivial factor. Okay, so it's fine. And the content of this theorem is that it's possible to draw similar pictures in all dimensions, where somehow things kind of transverse. They behave in a good way in the interior, they're transverse to the diagonal, and at the boundaries, they look like the previous thing, and so on. It's uninductive process. It's maybe not so, I'd say not so hard to convince yourself it's true, but actually writing it down is a bit, basically a generalization. Okay, and so what? So, so if we take this theorem and we maybe I'll make a definition. Definition. Given factorially factorizable space is a collection of maps x to n, sin and c. C here is some fixed V1 surface. It will always be non-compact. For example, like T star R. As such that let's say for a copy of T star 01 sectorially embedded into C, maybe avoiding some finite collection fixed. Well, you can ignore this now. Points C. The corresponding xn over C star. Let's put it like this. T star over sin and T star 01 has the following properties.
So this xi is the plural.
Yeah, they're restricted to this thing. So that this has the property that, so I have this cover that I described downstairs, so that the free images let's call this pi, and that's that pi n as pi and inverse of this kind of Joe sectors is U and L, C1, CK, and R is a sector. Okay, and factorizes compatibly with the factorization of these U's. Factorizes.
So different n, x n could be no relation.
Hmm?
Different n and
This
x.
imposes a relation. This says that over this U, xn restricted to that U is, after some deformation, the product of the lower xn's.
Or the lower x n's.
So there's this notion of factorizability, which probably introduced by Valence and Drinfeld in the study of quantum groups and so on. And what's behind this is kind of making some versions suitable for quantum groups. Factorizability means this kind of Okay, so this is the definition. And this kind of theorems. Theorem. Now this stuff are going to be these papers. For the rest of the talk, everything in these papers are argumentative. This is a paper too. Also, this theorem will also appear. It's a theorem. Given one, given let's say given a sectorially factorizable space. X and C, and inclusion E star 0, 1, and C. One, kind of the kind of direct sum of the chi categories of X and restricted to. What did I do? Sim and this thing. Strictly speaking, sim n of this thing is not going to be a sector. But this Zhou theorem I said before tells you how to round corners at the boundary to make it a sector. Okay, so you use that same kind of decomposition to make a sector which looks like this. So the direct sum of this is an algebra of categories. An algebra of categories. And two. So when you have this kind of decomposition, so here the whole thing is some C. This is this copy of T star 1. Let's give this a name. Let's call it I. Let's call this algebra A X I. Okay. Okay, so then similarly, yeah, this part, let's call this part F, and this part G. And so two, chi category of this kind of sim and X, sorry, the direct sum chi categories of X and restricted is sim and F. And again, you have to use this kind of Zhou cover to make sense of what this means precisely. Is a left A X I module. I'm going to draw this on. And the corresponding thing, I guess this is what's right. And the corresponding direct sum of product categories of x and we should update to sim. And g takes a left. A module. Here, and finally, 3, the direct sum of product categories xn isomorphic to okay, let's give this a name. Let's call this bold f equals bold g, bold f, that's it. And this is going to be derived. Well, that's the theorem. So it's some kind of exponentiated version of the gluing theorem in the previous talk. It happens over the symmetric product. And moreover, there's some kind of first example of such a space where this is the identity map. Okay, so a trivial example of sectorially factorizable space is sim NC itself. And for sim NC itself, this tells you that the Fukaya categories of symmetric powers of curves can be computed by some kind of tensor products in this way. And this kind of, so for x and equals sim and c, this probably is, this is some known TQFT structure on a Hegardt-Floer model. Because Hegardt-Floer is about Fukaya categories of symmetric products, and this is saying that this satisfies a gluing along open, along intervals. And I think the Hegardt-Floer people have their own names for it. I think it's like bordered Hegardt-Floer or something. But there's a paper of Ruquier and Mannion, which is somehow relevant to this question.
Is it the GR11 or something?
I think they're probably the same. Probably both of them. But anyway, what those guys do is they, the Hegardt-Floer people had already turned all of this, they computed everything in sight. And I think maybe also proved some theorem which maybe Ruquier and Mannion interpret as such a statement. Or maybe they proved this. I don't know. I didn't read their paper. But it has this flavor. So let me tell you. Why all this is true. Okay. Let me just maybe say kind of in words why it's true. The point is that I just got to draw a picture. The first two statements don't need all this stuff about this kind of special cover and so on. So those are true basically for the following reason. So if I have this strip, this kind of T star 0, 1, then this kind of factorizability says that if I take kind of x n1 times x n2 times so on, then I can map that into x kind of sum of the n's by sending it to kind of a, x n1 over a t star 0, 1, and so on. Well, I can send this guy to someone who lives in here, and this guy to someone who lives in here, and this guy to someone who lives in here. Okay, so that's an algebra structure. It says that the product of these spaces map to this space, and then just apply apply covariant functoriality of sectors. And you get, I guess I need the sector structure to say that, and then you get a map on the fact categories. And you get all the coherences because, I mean, you know, you might want all kinds of coherences or whatever, and those follow from this kind of compatibilities that I wrote for this optimization. Okay, so this is the algebra structure. And the module structure is similar. You just remember there's something sitting over there. And so then you can put the x's in and then make them back on this one in the same way. So the module structure is similar. And this tensor product, I guess I have to tell you what that tensor product means. Okay, so what is this tensor product? What is this tensor? So I remind you that if we were just doing usual algebra, then this would be some kind of totalization of some complex where you take F tensor G, so in usual algebra, not categorical. This would be some kind of totalization of some complex where you take F tensor G, and then there's a map from F. So this tensor is over A, but this tensor is over the field. F tensor A, tensor G to F tensor A, tensor G, and so on. Okay? And this is what's called bar complex. And I'm also, since this A has an augment, so in our situation, this A was like some A0, which was kind of just modules over the field, plus A1, plus so on, because there's a Fukaya categories of all the number of different powers. And in that situation, there's something called the reduced bar complex, where I only keep the positive part. Okay, so in usual algebra, I can compute such a tensor product by this reduced bar complex. And in the categorical world, so there's no such thing anymore as totalizing. This kind of complex doesn't make sense. You can't totalize it. But instead, we replace this by colimit, and that still makes sense. And I think someone's probably even proved, some category theorists probably even proved that this is the correct notion that you take, you do this thing. And the point is that this kind of sectorial decomposition of the symmetric product before has exactly this structure. So this kind of cover I gave. So let me just go back to this example. This kind of cover I gave, the biggest pieces were 0, 2. So this F tensor G would be the sum of the 0, 2 piece, this 1, 1 piece, and the 2, 0 piece. That's kind of the sum of this the biggest pieces. Because, and then the next piece will be this kind of, it's the diagram I drew before. I'm not going to do it. It's this, this is the one with 3 things, this is the one with 4 things, and so on. Okay, so it's, the point is that that cover exactly matches this structure. And that's the truth. So because of that fact, so this is a definition, this equality. I mean, it's a definition or it's a theorem of category theory. And this colimit equals the thing it's supposed to equal, by this existence of cover plus GPS. Because it's an example of a sectorial cover. Okay, so this is not, the upshot is, if you apply this GPS business to an appropriately chosen cover of something like, of something which has this kind of factorizable structure, then you get some setup where you get an algebra in categories, and you get modules for it, and gluing amounts of technical cover. So now finally we have to come full circle and give some kind of example of this. I mean, I told you one example already, which actually already contentful, which is the trivial example, which is sim and sim. But in the first few lectures, I was explaining that, so recall now, from earlier lectures, we had this kind of map from this Coulomb branch. And it sat over some T mod W, which in the case that we were interested in was some kind of product of symmetric products. So let's just say it was one symmetric product. And in our case, it was a C-star. Okay, that's the situation that we were in. And the kind of mechanics of this was that we studied this by drawing pictures that look like this. So this kind of zero, infinity, this was a picture of some star. And we have pictures that kind of like this, whatever. And so maybe I'll be a bit schematic. So theorem, there exists a similar story over all curves. So, I mean, one way to construct this similar story is just take the story we had over C star, ask what it does on a disk inside, and then glue that up. Okay, so that there's no, there's a stupid way to prove this theorem.
So again, it's the similar story for all.
So with C star replaced by other stories. And one way to convince yourself this is true is whatever the story was for C star, kind of over a local patch, it doesn't matter which local patch you took. Right? I mean, this kind of description was kind of not so specific. I mean, anyway, you convince yourself that if you take different patches, and it looks the same on the different patches, it's only special at how they intersect this kind of. Or in other words, if I take some disk C star, I can pull this story back to sim and the disk inside sim and C star, and you can convince yourself this behaves well for changing different disks.
So is that like the top space you construct by gluing, or is that like a global description
Of this one,
yes.
there's a global description. It's a Coulomb branch.
On any curve?
On any curve, yeah, so it's supposed to be some kind of open exhaustive. But whether whether we will, in the end, construct it by working out this theory or by just glue it in our answer.
So basically you should have the Coulomb branch for...
It's not a Coulomb branch. So okay, maybe I'll say the physical thing. So this Coulomb branch also has an interpretation as moduli of monopoles on C star times R with some condition infinity. And so in general, you take moduli of monopoles on surface times R with some condition on infinity, but that condition is a little bit annoying to write. And so as a consequence, maybe we'll write it, maybe we won't, and if we don't, we'll just do it this way. So now we'll glue together different charts. There's two ways to do it.
So again, so for any surface, then you will construct a holomorphic symplectic manifold with a
I don't
foundation.
know if it's holomorphic symplectic, but anyway,
That's something.
some at least symplectic manifold with a fibration which
That's not algebraic.
I'll say it this way. You could even make it algebraic, but the thing that's relevant is the following: that if I have some disk in C star and I take a different embedding of that disk in some other surface, then whatever item I'm making over this C has the property that if I pull it back this way, it's the same as if I pull this one back this way. Okay, that's the and if you want that property, you can just turn that property into a definition, assuming that when I change this disk around in C star, that somehow the thing transforms correctly. So there's a property you can check of this vibration, which guarantees that you can glue it together already.
So the choice is you start with the quiver and then you can do that for any curve.
Yeah, that's right. Yeah, the quiver thing is fixed. Yeah, so okay, there's some similar story, and it is
So what is the small n for the quiver?
this n.
This is a small n downstairs, right? And
So
upstairs.
to avoid confusing myself at this late hour, let's discuss this quiver. And so in general, it's not sim n; it's a product of symmetric powers. So for this quiver, it's literally a symmetric power. And of course, like taking products is easy. So it's the symmetric power part that's hard. So for this quiver, it's literally a symmetric power, and n would be sum over n. But n is the dimension factor. Yeah, okay, so similar story for all curves. It is factorizable. And now I just have to tell you.
And so all this work with W. Right? There's a potential function W.
Yeah, and compatible with potential function. And it's not compatible with potential. The kind of reason you should believe this, it's annoying to write down this potential, but the reason you should believe this is all the calculations I did on those first 2 days, they were drawing pictures on C star of like various curves there and some pictures in the fiber. And I could have done all the same things and replaced the base C star with any surface and kind of just follow the same rules. And in fact, you could try and define the theory like that. That's another approach to setting it up. Just like use that as the definition. That would be analogous to this this Robert Lipschitz definition of Hagar Floer. So nothing stops you really from trying to give such a definition. Okay, so yeah, this thing and. So now I'm just going to tell you what various surfaces give you. So this surface this surface gives you, when I take the direct sum of Fukaya categories of all these axions over it, gives you the categorification, this KLR categorification of the upper half of the quantum group. And the proof that this is true is essentially the same calculation as for this annulus I was discussing last time, because whatever the scalar categorification is, it's given by the same diagrams as I was using before, plus one extra move when I can stack them next to each other. Now we have that extra move. And this thing gives you this Webster's categorification maybe look at the n-axis of Webster's categorification of tensor products of simple modules.
So you refer to this summation of all the Fukaya
Yeah, summation of all the Fukaya categories. I mean, the different Fukaya categories correspond to different weight spaces. In
So
the,
what are the red thing again?
I explained it. It has to do with this potential, with the superpotential. I mean, just briefly, what is this red thing? Throughout, we're working with this Fukaya cap, this kind of round Fukaya category, so it's a potential function. And that potential function, it's the same when restricted to most fibers, but when restricted to fibers that involve these x's, then it's a bit different. Right? It kind of degenerates in those fibers. So those x's, they record the location of the degeneration of those. Okay, so this is the module. And so the point is that now, this guy, this is some trimodule. Okay? And a trimodule gives you a tensor product, gives a tensor product on the category of representations. Because if I want to know how to say, like, what is a trimodule? A trimodule is a map from A mod to A tensor A. Right? That's what a trimodule is. And maybe the other way around. A tensor A mod A. It's both things, but I'm using this one. And let's prove that it gives the correct tensor product. So it is the maybe I'll prove that it satisfies associativity first. So associativity.
Is it category or representation of the quantum group?
Yeah, no, positive. So associativity, like how I prove associativity? Well, I have to study composing this trimodule with this trimodule. Okay, what does compose mean? Compose means that I can tensor it over A. and I should compare that with the other thing. And tensor over A. But by the theorem, tensor over A is the same as gluing. And those are, so that's how this kind of exponentiated GPS gluing implies associativity of this tensor product. And let me just explain why it's the correct tensor product. So if you believe believed this statement, so by the way, let me emphasize in this statement that what Webster categorified is not the tensor product. He categorified, so he didn't categorify the notion of taking tensor product. He categorified the result of taking tensor product. So like if you take the tensor product of some modules in the quantum group, he gave you a category which decategorifies to that. He did not provide you an operation which allows you to tensor the different categorified representations. But that's why I put this in parentheses. However, now let's take this one and this one. So here are two different of this Webster's, okay, maybe let's put this. Two different of this Webster's categorified tensor products. In this case, there's no tensor product, or whatever, two different of these things. And now I apply our tensor product, and our tensor product is this object. Okay, and what does it mean to apply our tensor product? It means I somehow tensor over A. But tensor over A is gluing. Good. And therefore, our tensor product of Webster's modules is Webster's categorified tensor product of modules. Shows that you get the correct tensor product, and the kind of the proof that you get the correct tensor product is this kind of gluing formula. Maybe that's part of it.
So, a couple questions. First is, do they have a derived category perspective of this?
A derived category perspective. What do you mean?
Well, because the thing that you proved yesterday, you can do the B-side thing.
No, nothing I said today do I know a B-model story for. No. That's an easy question. No. Well, the question is hard. The answer is easy. Yeah, the question would be quite interesting to I'll make one remark. It's not directly related to that, but I meant to mention it, which is that, of course, you might want to know, can you produce this tri-module without all this story? So you might, so you could expect that there exists some algebraic procedure which takes whatever is associated with this guy, and maybe in this kind of general setting, to whatever is associated with this guy. And we have such an expectation. So let's recall that before we were doing this kind of exponentiated story, if we just had some kind of x sitting over this, so if we just had, in the old story where we didn't have all this kind of factorizing everything, we just had some some space sitting over this one, and I ask what's the, I add one stop and ask what is it, then the answer would have been that I take a category at C and I send it to the old kind of additive version. So I have a category C, and I send it to kind of a semi-orthogonal, it's a lax colimit on the map from C to itself. Okay? With this kind of exponentiated or factorizable version, there should be some similar formula which takes an algebra in categories A and it sends it to some kind of lax version of the tensor product. And we can produce kind of a formula for this as a bimodule, but not as a trimodule. So we don't actually know how to give. So we can give kind of two of the actions purely algebraically, but the third one we don't know how to give. Or one could instead ask for the kind of symmetry of this thing. We don't know how to do that. That corresponds. I mean, similarly, it's not apparent here. What is this kind of rotational symmetry of this guy? And what it is you like take some kind of element here, which looks like an element X, comma Y, and a map between them, and you send it to a kind of cone on the map, comma X, or something like that. It's some kind of this. Has a name, these functors, these reflection functors. And so we don't know, we don't at the moment know the corresponding reflection functors here. The reason I went on this discussion was that I could interpret your question as saying, could I just do algebra? Could I input this kind of quantum group and then just do algebra and get this result? I also don't know how to do that, and this is why I don't.
Because you don't have a cone constructions?
Hmm?
Because you don't have a cone constructions?
Well, I just don't know. I mean, I don't know what the analogous thing to do is. I don't know what the rotational symmetry applies next to. This is a temporal statement. If you ask me in 1 year, I probably will have the answer to this question. And at the moment, we don't know.
Can you say a bit more about this lax?
Not at the moment. I'd have to find my out.
So you get this categorification of this quantum group and all this. What is the physical theory?
Physical.
Yeah, is that a physical theory that's supposed to go with such a structure?
Oh, I mean, I think if you remember that one route toward this whole story was you begin with this Hayes-Witten 5D theory, and you go down to 3 dimensions. So you have something like sigma model in 3 dimensions, and that's where this Coulomb branch came from. So
Yeah.
Coulomb branch down here. But that same 3 dimensions now, if you put it not on R3 but on some surface times whatever, I mean, some other way of thinking about that should lead you to this. I mean, to do some further, like this is just saying, take those 3 dimensions.
Yeah.
Those 3 dimensions are T star R times an extra direction, and ask kind of what happens when you concatenate T star R's. And that should somehow teach you about the quantum in category. In the same way that some question in 3 dimensions should teach you about going to the boundary of Chern-Simons, you talk about the quantum group. Old mathematics, in the old days, now we have a theory which teaches the categorified story, and so we're just about here.
You say something about the grading?
Yeah, so I mean, this is kind of what I said in this second lecture yesterday. But, so as I mentioned, the location of these x's, they have to do with the superpotential. And the Fukaya category is locally constant as you vary the superpotential. So you could move the x's around, and you think the braid group on these x's acts on the category. But yeah, so you might ask, so what's confusing from this point of view is that I, so to speak, don't construct the braid group action using the code product. Like they're two different stories. And in particular, I don't know how to braid any modules except this kind. Actually, there's one more module that we know how to braid, which is, a different thing which gives you a module is this. Because whatever this is, you can also act on it.
So it's like a verb.
Yeah, this is the verb. So we can also braid the verb.
So what structures on the skeleton itself does
I don't know, incompetence. It's I mean, I do not know how to compute the skeleton of the symmetric power of a Riemann space. And I also don't know how to compute the skeleton of the Coulomb branch. I think, I mean, people have tried, but if you can do it, then do it. In particular, we don't have as I think I mentioned, for this Coulomb branch, we did not prove that we've constructed the generators of the category. And if we knew a skeleton, then it would be easy to prove such a thing. Because you're always generating when one person transfers to each component of the skeleton.
So it has a picture of any curve. So usually I would expect some E2 structure, we don't care about the algebra structure.
So I can tell you what I believe about this. So there is a in the literature there are two kinds of gluings of Fukaya categories. One kind is gluing along this interval, but there's a different kind which is gluing, which in this dimension is gluing along circles, and that's it's not in many places. It has it's only understood for surfaces, and for surfaces it's understood by Heather Lee or this Heather Lee. But it's possible that for these things sitting over surfaces, and this kind of like factorizable whatever, there's an analog of this circle gluing. And then,
But that is not, so what we should do, so how do we,
like just for Fukaya categories of surfaces themselves.
but no,
No, gluing for Fukaya categories of surfaces. And then you can ask about gluing for Fukaya categories of symmetric powers of surfaces. And then you can ask about for this like factorizable storage. If we had, so if that was some kind of world which existed, this would be an algebra object. I think actually already we know this is an algebra because you can just like put many. Yeah, I don't know. You could imagine some sort of gluing along this guy. Yeah, I know what that story would be. But if you had such a story, then you could start talking about the E2 structure.
What structure?
E2 structure. Because if you had a story where you could glue along this thing, then you could move that around. But we don't have that.
Is a story like, it's just a story, because no one cares, or is it difficult? I don't know. It's,
Proving a gluing theorem with Fukaya is difficult. you know, proving gluing theorems in the quadratic category is not, it's, you know, you need to do some geometry.
I have one last question. So contour group is bi-algebra. So you have algebra. So I guess it's related to this thing.
So a bi-algebra structure is the same as having a monoidal structure on the category of module for an algebra and a forgetful functor. This categorified story is not a bi-algebra in categories because how to say it? Being a bi-algebra in categories would be the same as asking this thing to be isomorphic to A tensor A. Okay, and there's a map. The reason that I say this lax, I mean, one reason to call that lax is there's a map from A tensor A in here, which looks like this. So A tensor A goes in here like that. And this map is an isomorphism after passing the K theory. Because all that's saying is that that's this kind of, I mean, that's this kind of a factorized version of this discussion I was having earlier, which is that if I take this object and this object, then the cone on them produces this object. So in K theory, they kind of, the story is already there, but here there's a kind of morphism between these two copies of A. That's why I read it like this. And so, yeah, so it is, for this reason, this is not an algebra structure, but it decategorifies to an algebra structure. So it's, in the literature, Alan Weinstein wrote some paper where he decided to call such things, but you could also ask about the Hopf structure or whatever. He decided to call things which have the property that your module category is monoidal and whatever corresponds to Hopf, but not necessarily with a forgetful functor as Hopf-Fish algebras. This is a Hopf-Fish algebra.
Yeah, so as I mentioned, we also have this very similar but not with the current family. I think the expectation is that A is actually a lax algebra. So you have multiplication and computation that lax the
Yeah. So there's a map from this. If by lax you mean there's a map from A tensor A to this trimodule.
No, more like the map from A to A tensor A. But I don't know your description of the lax in the map time.
Yeah, maybe we should discuss it.
So it seems like complementary somehow, but it's a description of what we got with the kind.
Further questions? Well, thank you for this